Good morning. Good morning, everybody. Good morning. And welcome to this plenary by Cecilia Kilhamn. Cecilia, she works at the National Center of Mathematics Education, situated at the University of Gothenburg, full-time now. She has managed to do a lot, I can see. She has presented and published papers at conferences such as PME, CERME, and NORMA. She's written journal articles, also including at high-ranked journals. She has written book chapters, she has edited books. She's also the editor of both Nämnaren and Nomad. And she has covered topics such as number sense, early algebra, and the last 5 years she's been part of a project on programming and computational thinking, and that is what we will hear about today. So we are looking forward to listen to you, Cecilia.
Thank you very much. Thank you all for coming, and thank you for inviting me. I was very excited to be invited here because I have a special place in my heart for NORMA in Copenhagen. 2008, I was here presenting my very first paper as a PhD student, and now I'm back here. So I'm very happy to be here. And I've been I'm going to talk to you about researching the implementation of programming in school mathematics in Sweden, based on a 5-year project that I've been doing. But I want to start to say that I was supposed to be not here alone. I was supposed to be here with my colleague Kajsa Bråting, and maybe I'll do it this way then. Nothing's working. There. My esteemed colleague Kajsa Bråting, I'm giving this lecture in memory of her. We worked closely together for 5 years, and she sadly passed in January this year after a short time of illness. We submitted the final version of our final paper in December, and the project formally was ended in December, and just 3 weeks later she was gone. So that was very, very sad, and I hope she's with us in some sense. So how did it all start? Well, I was invited to be a guest researcher at Uppsala University 2018, and at the same time the new curriculum had come about programming being introduced in schools. Both Kajsa and I had a background in researching algebra learning. And programming was put into algebra, and we were both surprised. So we said, what? We have to do something about this. We have to research it. What does this mean? What will it entail? How will it change algebra? How will it change school? What will happen? So that was our initial question. And we brought Lennart Rolandsson, who is a didactics in technology didactics, and he knew more programming than we did, because we weren't very proficient in that. In fact, I am so old that I missed out all programming in school. When I was in upper secondary school, the first computers arrived, and a small computer room was put up, and we were invited to come there and do some programming in BASIC. And of course, I was curious. I went there one day, and it was made very clear to me that this was not a place for girls. So I left, unfortunately. But 40 years later, I'm here now talking programming, so that's nice. We've co-authored in the project with some others, for example, Rima Nyman in the last paper, and Ola Helenius and John Mason in one paper. They were on our advisory board. And also Raimundo and Andreas from Denmark, who wanted to make a comparison between the countries. And before I go on, I want to say a special thanks to the EFOS project. I will talk more about that, and Eva Norén and Jalal Nouri, because they shared a lot of data with us. And of course the Swedish Research Council for the money. So setting the scene around 2018, the implementation of programming in school curricula in both England and Denmark, they were thinking about making it a subject of their own. In England they were first out making a subject called computing, and in Denmark they're trying out teknikforståelse as more of a pilot way. In Sweden, Finland and Norway, the programming was introduced across the curricula, but very much into mathematics. and in Sweden in particular in the core content of algebra. So the situation in Sweden was that 2017 the curricula was introduced and early adopters were allowed to start, and there were some who were very enthusiastic about this. And then 2018, just a year later, everybody was supposed to be teaching programming from preschool to upper secondary school. There was a very insufficient professional development supplied, some small courses, but not for everybody. No money for those courses, or no money or time for the teachers to attend them. There was no pre-produced teaching materials supplied, and no recommended tasks or platforms or anything. It was just all up to the teachers. So what were they supposed to be doing? This is what they were given. In grades 1 to 3, students were supposed to be learning how unique stepwise instructions can be constructed, described, and followed as a basis for programming, and the usage of symbols and in connection with stepwise instructions. In the upper grades, the stepwise instructions were changed to algorithms, but algorithms were defined as stepwise instructions, so really no difference. And then it was distinguished that they were supposed to be using visual and different environments. What does this mean? What did the teachers do? Well, first we wanted to look into the name of our when we applied for, when we started thinking about this, was how did algebraic thinking and computational thinking interact? And so we started theoretically trying to look at the intersection of these two. And I know Uffe was a guest professor at Uppsala. He started there at that time, and he said, well, what if the intersection is empty? And we said, well, in that case, that's what we'll find out. But we started looking into it more on a theoretical basis, and we found that it's not empty. There are a lot of intersections, but these intersections are not self-evident. They bring along a lot of contradictions and difficulties and dilemmas. And so after the first two papers, we decided, well, we went into the classroom and did empirical studies. The theoretical frame for our project was Trevalad's idea of transposition of knowledge. So he says that knowledge is can be described in terms of a praxeology, and the institutional knowledge or the scholarly knowledge, that's one kind of knowledge. That's the knowledge of programming for programmers, for mathematics using programming in their daily work, and for scholars and developers of programs. But if you move that into school, then it has to change. A lot of decisions have to be made about what do we bring in, what type of tasks, what concepts, in what order, and how do we make this teachable? And the first step is, of course, the curriculum, and then it goes on. But then the teacher reads about this and learns about it, and then brings it into the classroom. Then again it's transformed, because different things work and you interact with the students. And then in the last phase, what the students are actually experiencing and what they learn is, of course, depends on their background and what they know before. So again, the knowledge can be described in a different way. We didn't really look into the first phase of the scholarly knowledge, how that was transformed into the curriculum, because that was not our question. We had the curriculum, that's where we started. But we did try to find out, because we were confused. Why was it put into mathematics and into algebra? What was behind this? And we did ask around. We haven't published any of this because it's only, bits and pieces of conversations with people. And it's not easy with the government and the people who have decided that they don't really personally take responsibility. So it's the group, or that's what it is, and the people who have been behind it, you don't really get to know them. But we've spoken to a lot of people, and there seems to be, I think that there might have been a lot of lobbying from people who are going to earn money on this, because schools had to invest huge amounts of money in hardware and software to get programming going in schools. So somebody must be behind that, I'm quite sure. Influencing government and the Department of Education and so forth. But why in mathematics? Well, it seems some of the answers we got was that if we're going to teach, somebody has to teach programming, and if we have it from preschool to upper secondary school, how are we going to get teachers that can teach it? In upper secondary school, there was an electable subject of programming, and you had to have 60 credit points to teach that, to be formally certified to teach it. Oh, 90, I think, 90 credit points, university credit points. And how could we suddenly have teachers from preschool to upper secondary school with that kind of knowledge? We didn't, so we put it in mathematics, then suddenly all mathematics teachers were formally credible to teach programming. So, problem solved. And why, if it's in mathematics, was it not made a core content on its own? Why is it put into something else? Well, the only answer we could find there was that if it's a core content, there has to be learning goals and levels of grading appropriate for each grade level. And I don't think anybody had a clue of what that would be. So, putting it into mathematics, you didn't have to change the learning goals. It's still algebra. And then why algebra? Why not number sense or problem solving or statistics, which I think would have been probably the most, the one I would have picked. But then I spoke to somebody and she said, we discussed it a lot and it seemed to be the least bad solution. And anyway, there are variables in both algebra and programming, so it's more or less the same thing. And this is the base we give to teachers. This is what we expect teachers to understand and work from. That's quite surprising, actually. Then we went on to do our empirical studies. We'd studied in the second phase, the textbooks, what came into the textbooks. And we studied the teachers. We called them, the first teachers we studied were the early adopters, those who started already 2017 or at the beginning of 2018 with a lot of ideas. They were enthusiastic. They liked this. They said, oh, finally, something nice in mathematics. Some of them knew programming, but not all, but they were very enthusiastic. Often they were what we call first teacher or master teachers. They had the responsibility for developing mathematics or IT in their schools. And so we got hold of them, 20 of them from different parts of the country and different levels of the school, and did deep interviews with them. And our intention was actually to follow up on that and go into their schools and look at what they were actually doing and what the students were doing. But then the pandemic struck, so we couldn't do that. And instead we were able to share data from another study, which the people there didn't have time and interest to analyze, and so we analyzed that lesson study data. I will talk more about it. And in the end, we did more of an exploratory analysis of some of the tasks that the teachers presented to see what potentially could be in them. So for anybody who wants to pick up the after me, you can go into the classroom and see what are the students actually doing. Before we go any further, I want to you want you to look at this slide. It was produced by Lennart Börjesson, who was also in the project. He's more technically interested. And don't look at the details here, just to see that in the 80s there was a big development of computer hardware. And of course, we tried to put it into schools. We had in the Swedish schools, we had the Compis computers between 82 and 88. A lot of money was put into that, and they never really caught on, and now they're extinct, I think. We can see that the operating systems have developed and the programming languages. Java came in 95, and I think Python is not here. I think it came 91, and those are the most common ones used today in the Swedish schools. We see that the curriculum courses, there were several attempts at bringing this into the curriculum. They were called like datakunskap, programmering, and datorkunskap and datakunskap. Well, computer science and computer knowledge. They invented a very good word. I really like the Swedish word. It's called datalogiskt tänkande. Translates as data logic knowledge, instead of computational knowledge. Because to me, that's more what computers really do, what they're good at. They're good at logic and they're good at handling data. But for some reason, this is not part at all of the current curriculum. That word was sort of thrown out the window. And what happened then after 2010, from which this overview gives you? Well, our early adopters, they go out on the internet, on social media. They use Facebook, they use YouTube, they get their communities of practice on Facebook, and that's where they get their ideas. They use Hour of Code and Scratch as teaching materials, because that's what they had. They had nothing else. And the curriculum decided programming and stepwise instructions. That was it. That's what we want. The environments or languages were Python, Scratch, and then GeoGebra. And there's a debate whether or not working with GeoGebra is programming or isn't programming. In Gothenburg, we have Thomas Linjefjärd, who is very strongly into GeoGebra, so he gave courses and programming courses. It was all about GeoGebra. Some teachers said that I like GeoGebra, we do GeoGebra, and so I've done the programming. And others said, well, that's not programming. That's not a programming language. We can't use GeoGebra. So they didn't know. The hardware is, in Sweden today, we have personal computers on a one-to-one basis in very many schools, I would say almost all schools today. In the lower grades, it's usually an iPad, not a PC, and the Chromebook is one of the most common, I think, as far as, at least when I go out in the schools, that's all I see today, Chromebooks. So that's the setting for us. When we interviewed the teachers, we had these 20 early adopters. They rely so heavily on social media. We were just struck by that. Don't you have anything else to go on? No, but Facebook is great. I mean, this group and this group and this group, and they give me such a lot of good ideas. The mathematical content that they talked about when we asked them, what do you do? Can you show me some tasks? Why is this a good task? And why do you do it in mathematics and that sort of thing? It was all about geometrical shapes, some calculations, probability and statistics. Nobody did anything that they remotely related to algebra in the way they talked about it. So I don't think, maybe they didn't see that it was in the core content of algebra. They didn't really notice that at the beginning. To describe knowledge, Chevalard uses praxeology that consists of logos and praxis. The praxis is the know-how, and he describes types of tasks and techniques of how to solve these tasks, problems to solve, situations to deal with, and how you do that. And then the logos part is in two parts. It's technology, is the reasons or the arguments why these techniques are used for these tasks. So why do we do that? And the theory is more, why do we rely on what we do? Why is this good to do? What's the goal, the end goal? What's the theory behind it? What's the epistemology of this knowledge? And this praxeology can be applied to all kinds of knowledge and at the different stages of the transposition. So we thought that they want us to have a reference epistemological model, like what would the knowledge look like in the ideal world to compare with. And we thought, if the ideal world is like somebody who wants to use programming in mathematics, then what would it look like? And we thought that the tasks would be like data handling, statistics, proofs, modeling, test outcomes, calculating results. The praxis would be different algorithmic techniques, sequencing, and tinkering and remixing, debugging, that sort of practices that computer programmers do. And the technology is, why do we use these techniques for these kinds of tasks? Well, it's because we want to use the power and the speed of the computer. And if what we do, it does not give us power, or we don't need the speed, then that's no reason really to use those techniques. Then other techniques might have been better. And the theory behind it all is that logically constructed, unambiguous steps of actions give us trustworthy and repeatable results. We believe this. And if we don't believe that, then all the computer does is of no use. So this is a logos that we think you need to understand about programming. But this was, of course, not given to the teachers. In fact, Morten Misfeldt and Ola Helenius, they made an analysis of the comparing Denmark and Sweden. They said that the Swedish curriculum actually didn't have any logos at all, or hardly any. Nobody talks about why do we do this? For what's the reason? Why should we believe it? Why should we use it? And when we talked to the early adopters, we asked them a lot of things, and they talked about praxis. And they talked about what programming language is, but they didn't really talk about explicitly their logos. So we tried to analyze what kind of underlying logos could we see here. And we saw 3 different answers. So one group of teachers, they talked about tasks that were about learning to communicate with the computer. How do I get the computer to do what I want? How do I get the robot to walk? That was the task. And they talked a lot about algorithmic thinking, coding, and syntax. I need to learn the language of the robot, or the program, or the Scratch. And they used the types of languages that was prescribed in the curriculum. So did it say visual environments? And they said, well, I have to find out what a visual environment is. Oh, it's Scratch. Okay, I'll use Scratch. So we interpreted their logos in this way, as the picture here, that they talked about programming as an important part of digital competence or digital literacy, but mathematics was sort of left out. It was something else. Now, the second group of early adopters, they talked in a different way. They talked about coding tasks, really learning to code. They talked about CT practices like tinkering and remixing. We're fostering coders. We're making people good programmers. And they said, well, when I choose what environment, I want to have an environment that is easy to learn, because I want them to learn to be programmers. I don't want them to be hung up on the too difficult syntax. And one teacher actually said, well, I believe programming is at the heart of mathematics, because it's about logic, it's about sequences, it's about calculating and getting trustworthy results. That's mathematics to me. And so their logos is more like mathematics. There's no dichotomy between programming and mathematics. Programming is a kind of mathematics. And the third group, they talked about mathematical tasks. And they talked about using mathematical problems and solving strategies, exploring mathematical concepts. And they said, well, I have to use a programming environment that's useful for doing this. And this is where we find teachers who think GeoGebra was a good program environment, because GeoGebra is actually developed for exploring mathematics. And if that's what you want to do, then that's a good environment to choose. And we think that this is how we interpret their logos. They think that programming is a useful tool that we can make use of in mathematics. And of course, I don't know what the government thinks, and I don't know what we as researchers think it should be. But for teachers, they might benefit from making these things explicit, making them aware of what do I think here, what do I really want, and why do I do these things. So we went in to study the teachers' voices. After the earlier adopters, we got into contact with the EFOS project, and they had gathered or organized groups of teachers who wanted to learn about programming. They didn't know. These were normal teachers. They were, what do we do? Well, one good thing would be to go together in groups, do a learning study, try to develop a good lesson, and we can arrange this in a format for you to develop this. And so they all came in with documentation of what they did, and had a big seminar which we could attend, where they presented their lesson. So like, an iteration of a lesson study, doing it several times and coming up with what they thought was a fairly good lesson. And then we were allowed to analyze these documents. So I haven't been in this classroom, I haven't been developing the lesson together with the teachers, but I've looked at all their documentation and analyzed that. So 32 lesson studies, so quite a large number of teachers involved. And when we did that, we developed a framework describing the relation between mathematics and programming, because we thought that was quite different in the different lessons. And the relationship, one relationship was that there was none. There was just about programming. They never mentioned mathematics. One teacher, I remember, she said, or one group, they said, well, we tried mathematics, but it was actually much easier to do the programming in Swedish class, because the children wrote a story, and then they went into Scratch, and then they did an animation of their story. And they did that on the maths lesson because it was programming. So another one is mathematics is a context for programming. So we do programming, and we do it in the maths lesson, and we do some calculations or some geometry, but the goal is not to learn the calculations or the geometry. I know that already. The goal is to learn programming, but it's in the context of a mathematical setting. The third one was tasks where the program was a useful tool for efficiency, as I said very early on, that's actually the logos of programming, that it is efficient. That the computer is very efficient. And some of these lessons, they use this efficiency. And the fourth one was when programming was used for exploring mathematical concepts. So this was a way of describing these lessons. And what did we find? Well, I'll give you some examples first. This is an example of what we said, this is no programming, no mathematics. It's a task about building a lighthouse using a microbit. It's a task that is, the teacher was teaching both mathematics, or the teacher groups, they talked about mathematics, but they were also teachers in that group who were teaching technology. And this is a task that they would have done before the programming was introduced into the curriculum in the technology class. So it's not a case of learning any mathematics here, it's a case of learning to make the microbit turn the light on and off. Another, what we see, not really any mathematics involved, is very often in the lower grades, they did stepwise instructions. Instruct your friend to move across the room. Instruct the B-bot to go from here to there. Move around, and very popular was a dance program. Make a dance program in Scratch. Create a nice sprite. Give it some clothes. Make some nice movements and some sound and music, and now you've been doing maths. So we say this is not really maths, is it? It's okay, there's some programming in it. So if you have the logos that programming is actually mathematics, then okay, you can say it's maths, but we didn't really see a connection here between what we call mathematics and programming. This is an example of mathematics as a context. It's from a group in grades, with teachers in grades 7 and 8, and they came up with this piece of code. You can see it's about variables, and it's about teaching the computer to save the value of a variable. And the context is to calculate the area and perimeter of a rectangle. And in grades 7 and 8, you know how to do that. You know this is no new mathematics. It's not about exploring the perimeter, but it's about learning what it looks like in the code. And actually, it's not very efficient either, because, I mean, if you just want to calculate the area, you can just as well use a calculator. Why have this sort of complex code? You have to look into and understand what it says, unless the goal is to learn the syntax of the code. And actually, if you wanted to learn more about the mathematical ideas, I think algebra is much more efficient. Working with these kind of formulas, you can discuss, well, what happens if the length suddenly is twice as big? What happens with the area and the perimeter? You can see that here. You can't see that here. You can investigate it empirically with the code and get a lot of values, but you can't see it theoretically. You can't do any more mathematical argumentation around it. And then finally, this is an example of exploration in mathematics, at least potential exploration, because this code was given to the students or shown, and it was also shown what it did. And then they were asked to reproduce it on their screen. And this was the first time they used Scratch. So most of the kids, although they did the iteration 3 times, they didn't really get much further than actually reproducing that code and getting the code to draw this nice circle, this red circle. But the idea, the potential in the task that they wanted to keep working on was that the next step is to tinker with this code, change it so that it will draw a circle that is half red and half blue. And then you'd have to go into the code and see, what do I have to change? What are the variables here? And this is an even more advanced one with 4 sections. So here you could explore a lot of things about. In grade 6 it's relevant. How do I explore the circle and sections of the circle, and what do I have to change, the angle or the width or whatever, if you get there. So this is what we found. Don't look again into the details, but rather the big picture. First you can see that there is 10 of the 32 lesson studies where there was no program, no mathematics, there was just programming. You can see that when mathematics is a context for programming, that's also 12 out of the 32. It's numbers, calculations, or geometry. That's a good context. It's an easy context to use if you want to learn programming. If you want to use the efficiency of the computer, then statistics and probability is the context that the teachers found useful, mainly. And also you notice that nobody picked algebra. Nobody said, we're doing an algebra lesson. But if I asked them, they would have said that we're doing algebra because we're doing programming. So what challenges did we see when we looked at all these together, these 32 lesson studies? What challenges did these experience, the students, the teachers, and their headmasters that were also part of the conference that they were supposed to help them develop? What were the challenges? Well, the first challenge was, of course, the teachers' own lack of programming competence. Most of them had never done any programming or done a very little bit of maybe some basic programming sometime at school years ago. They didn't really know what they were supposed to be teaching. The other challenge was accepting failure as a resource for reflection. Now this, I think, is something we could learn from in the mathematics education, learn from computing and computer programming, that at least in Sweden, teachers are very, very afraid of letting students fail. A failure is not good. We want students to answer correctly. And if you don't want to call on somebody, I think Deborah Ball spoke a lot about that, we don't want to call on somebody who gets the wrong answer. But if you're a programmer and you work with code, it's part of the natural flow of the work, that you run the code, it didn't work, you see what you have to change, and you run it again, it didn't work, and you do it again, and you collaborate with others. I think that's a really good practice that we could import into mathematics teaching. But it's not part of the frame of mind of the teachers or the students as it is in the mathematics classroom. The next challenge was all the side effects, especially with Scratch. I mean, Scratch brings along so many things that kids think they are fun. That's a lot of nice animations and sounds and clothes and colors, and all the focus is on them. And of course they are, because Scratch is not developed to be a teaching tool for mathematics. Scratch is developed to be something that engages students in engaging with a computer. That's the whole point, and they do, and it's good fun. But it distracts attention away from whatever learning goal you, as a teacher, might have had. And then, of course, it's a time issue. It takes a lot of time to learn to program. And you have a certain amount of lesson time for mathematics. How much of that are you going to spend on programming? And how much of your own time, your own free time as a teacher, are you going to spend on learning to program so that you can teach it? So the time issue is a big challenge. The next challenge is the unclear relation to mathematics. I've talked about that. What is the logos here? How do I relate this to what I'm doing in mathematics? We need some kind of consensus here, I think, for the teachers. And then, of course, the last one is where we started our project. What are the similarities and differences between, for example, variables in algebra and in programming? Because they thought, some of the teachers in the lesson study, they thought they were doing variables, but then they realized, we could see that in the documentation, that, oh, wait a minute, what's this? So both variables, and I think even the function concept came up as one of those problematic concepts, because they meant different things in the different environments, or in the different contexts. So I want you to take a minute, think about, and maybe talk to your neighbor. What is the difference or the similarities between variables in algebra and in programming? So I'll give you a minute or two for this. All right. Please finish off what you're saying and focus again up front. I've got you thinking, I could hear that very much, thinking and speaking. We thought a lot about this in the project. What are the differences really? And are they superficial or are they real differences? One of the obvious differences is how we treat the equal sign. In algebra, we could not write x equals x plus 1. We would say that's an inequality. Because the x in a formula in algebra, the x, it's one of the fundamental things that students need to learn. If there is an x several times in the equation, it's always the same x. Whereas in programming, x equals x plus 1 is perfectly normal to write, because the x's are different. The first x is the new value of the x, and you assign the new value, which is based on the old value of x. Now this is, I don't think students have, it doesn't necessarily have to be a problem for students that this can be treated differently in the different environments, but it's something we need to be very much aware of as teachers and problematize, discuss with them and compare for them so that they see these differences. In school algebra, a variable is always numerical. Now, it doesn't have to be. I did my master's thesis about function boxes, and in these function boxes we had variables of all sorts of kinds, very many language words and letters and things. But in mathematics, in school algebra, we always work with numerical values. And one of the things the students learn is that behind the x is always a number. That's one of the important things. And then we have a lot of research done on what kinds of variables they could be. Sometimes they are unknown numbers, sometimes they are placeholders or general numbers, like in the when we say the commutative property, for example. And sometimes they are actually varying quantities. But in programming, they are storage places for values. That's something quite different. And they are often numerical and non-numerical, and in all the lessons we saw, the first variables they meet are all non-numerical. There are colors and shapes and sounds and all sorts of things. And they can be varying and non-varying, and they change during the process in the code, so they're not the same. So this is a difference. Another difference, or some other differences that we saw, are that in programming, things are very explicit and they're very specific. Whereas in school algebra, we talk about abstract and general things. In programming, things are approximate. Pi, for example, you have to decide how many decimals of pi you want to put into the computer. Whereas in algebra, you just write pi. You just write pi, yeah. You just write it, and it's there. It doesn't have to approximate. It's precise. I don't know it, but it's precise. The program is stepwise and dynamic, as the circle you can see here. There's never a whole circle. The program has to make the circle one step at a time. In school algebra and geometry, we speak about the abstract circle. It's always there. It's defined as all the points that are at the same distance from the center. So it's static. It's there. Program is time dependent, and school algebra is time independent. So the overlap is there, but there are some very big and important differences between how we speak about different things in these two environments. And this was not anything that we could see that the teachers were aware of at all. Right, time is going, but we'll have time to talk a little bit about our textbook studies. We did first a paper on the analysis of textbooks from grades 1 to 6, and then on textbooks from grades 7 to 9, and then a comparison with Denmark's. Some similar material. They don't have textbooks because it's still on trial, but materials for the same age group. And what did we find here? Well, our question was, what characterizes a programming context in the Swedish textbooks, and in what way does it create a bridge between programming and mathematics? We looked at a lot of textbooks, 390 tasks in grades 1 to 6 and 386 in grades 7 to 9. These were all tasks that were in some way labeled as being programming tasks. I'll just go back and say, we also looked at these in the 7 to 9. The publishers produced some specialized books which were only about programming that you could also use and bring into your classroom if you wanted. Some teachers brought them and some didn't. And here we also analyze the units, and a unit is like a chapter in a book. We start very often at this grade level there are subtasks that create a bigger task, so we had to treat them as units. And the 380 tasks were found in 62 units. We were inspired by Benton et al., who from the Scratch Math project, who developed a framework for designing tasks using the 5 E's, as they said. That was very fancy, and we tried to copy that. We weren't as successful, as you will see. But we were doing analysis of tasks that were not based on this design. So, of course, these didn't fit completely. And the first one that didn't fit, that we had to invent, was that the action asked of the student was very often to follow a procedure. Just follow the instructions, run the code, and see what happens. And that's not in their design principle. And so we started with F, and we came up with figure out. It's quite a lot of tasks that you have to think. This is the thinking action. The first one was a doing, and this one is a thinking action. Think about it, figure out what's happening here, what is the rule, what is the pattern that is described in the code. Find the mistakes, or this means debug the code. Form and create. Now we're getting into trouble with the F's here. Write a code, give instructions, create a pattern. That's, start from scratch and create something. And now we ran out of F's. So we have explain the procedure using natural language. Now this is quite a common type of task. And we kept the envisage. This is again a thinking task. What will happen if we change the code? Not instead of change the code and see what happens, what will happen if you change the code, or if other assumptions are made. And in the later grades, there were also a lot of tasks with tinkering. Just change the code a little bit and see what happens. So it's not the same as follow a procedure. It's not just run the code, it's change it. And this is how it came out. You see the blue in the bottom, that's the grades 1 to 3. And then the orange is grades 4 to 6. And the green is 7 to 9. And you can see that follow a procedure is absolutely the very most common task. Just do it. Here's the code, just do it. We can see that tinkering was only in the upper grades. Envisaging is very, very rare. And debugging is also quite rare in these textbooks. Either you follow a predefined code, or you are asked to write a code yourself, or write an instruction of some kind. Here's an example of a follow-a procedure. So it just says, follow the instructions, draw the robot, how the robot walks to the package. And you do it. And this type of task actually caused a dilemma for some, because in some tasks it doesn't, here it says go 2 squares, but in many tasks it says go 2 steps. And this is a stepwise instructions, but the steps here, are they the steps of the program, or are they the steps of the robot? So the steps have double meaning here, which is a bit confusing. This is another one. So this is all in a textbook, so it's not on the screen, and they have to draw it instead and imagine the screen. And now they introduced a loop, and they are asked to, but it's still just to follow a procedure. Do what the loop says, and then see what happens. And of course, a square is created. And in 5th grade, you know what a square is, so it's now really mathematically interesting. This is a figure-out kind of task, but here we can see some kind of bridging, because this task, the identical task, was in the same version of the textbook before the introduction of programming, except that then they didn't have write with a code, as it says here. So it says, here is a repeated pattern, find the repeated pattern. That was the old task, and now it says describe it in code. And I don't know what they think the code is going to be here. The student has to invent a code, but that's the idea, I think, from the curriculum, using symbols to express something. So the kids are supposed to find the pattern and then somehow describe it in something that looked like a code. So here's a way of trying to bridge what was the algebra content before, and now we wanted to bridge to programming. So how can we introduce programming in the same setting? Here's another more advanced way of bridging into programming, I think, because this is one of the tasks that we actually liked very much. I think it's our favorite task. They were given the code, so they don't have to come up with all the syntax themselves. And it's about finding prime numbers, which is, this is years 7 to 9, so it's good mathematical ideas for that age to really see how many, if you go, they know what a prime number is, but if you go up to big numbers, we can use the computer efficiently to do that, and we can investigate what happens with prime numbers. And so they are exploring the concept of prime numbers in this, and they are asked to follow, and then to tinker, and then to debug, and then to envision what will happen if. And in the end, they are even asked to go out on the web to use the community. So this is a very rich task. It's mathematically interesting, but it's also programming, and it's using the efficiency of the program. And the relation between mathematics and programming in these textbooks for grades 7 to 9, then we had to look at the units to make any. We tried the tasks, but it didn't work because the tasks are often subtasks that are building up in a whole unit. And so we analyzed them in this following way. If there was something about exploring mathematics in the unit, we coded it red. If that wasn't the case, but there was something of using the computer as efficient calculation tool, then we coded it blue. If that still wasn't the case, but there was some mathematics, we coded it purple. And if there was no mathematics, it was green. And it turned out that 13% of the units had no mathematics. It was particularly in the books of the specialized books of programming. They would start with a whole unit of tell the computer to say hello, hello world. You know, that's how you always start. 74% of the units had mathematics in them only as a context. Nothing new in mathematics for the students to learn. 3% used mathematics efficiently or programming efficiently. And 10% actually, that's higher than we thought when we started, had some exploration of mathematics. But this is grades 7 to 9. It's much more difficult to have some really interesting exploration tasks in the lower grades because they know the mathematics there is more simple and the computer only confuses that simple mathematics. The comparison between Denmark and Sweden, I'll do that very quickly. We looked at what concepts were brought up, and you could see that the curriculum had influenced the Swedish textbooks very much. So a lot of talk about instruction, and loop and repetition is one of the few programming computational concepts that come in. And of course, algorithm, that word is mentioned a lot. In Denmark, data is more prominent, and program as a concept itself. So they take a broader view. And their mathematical concepts are also different. You can see again, pattern and sequence. I think that's because it was put into algebra, and we had patterns and sequence as an early algebra topic in the early grades, and then they tried to connect that to programming. There's some geometry and some statistics and in Denmark. But there's a big difference here, which you see the actions. We looked at all the tasks with that had mathematical concepts in them. And we could see this as percentages. You could see that this follow instructions is very dominant in the Swedish data, and not so much in the Danish. The Danish data is much more of explaining, using natural language, explain what happens in the code, or envisage what will happen if you change something. So there's a difference there. Now I'm going to come into the last paper we wrote, or not the very last one published, but the last one we were working on analyzing. This was, if you might recognize it from one of the lesson studies. It was a code which we thought had potential. And we said, well, if we really tweak this, if we really work on it, with all the knowledge we as mathematicians and mathematics educators and programmers have, what could we do with this task to really make it a rich exploration task? Well, the first thing we thought was to make all these variables that are in here that are implicit as variables. We make them explicit. So you can see there are so many variables here. You have the go-to, the sprite position, the point in a direction, the sprite rotation. You have the pen size, the pen color, the pen location, and they have the loop counter. All these things are variables, but in the Scratch environment, a variable block is orange. Those who look orange are actually yellow here. So there's no variable block used. So there's no explicit variable in the code. So one of the things we did was try to bring in them as explicit variables. So we introduced the variable radius, number of rays, and I'm going to show you because you won't understand otherwise why these variables are here. I think I managed to do this yesterday. Yes, here we go. We press it, and this is what it does. Very exciting. And if I look inside, and I decide to change, for example, the number here to just 20, this is what it does. So you can work out what it does. It goes from, it paints a ray from the center out and back again, and then the next, it moves, turns a bit, and the next one, and the next one. So I'll try to get rid of this. Here we go. So by making these explicit, we could start talking about these variables and see what would happen and envision what would happen if we change them. This is not working. What would we have to change to make it look like this? Or this? Or this? And when is it a circle? What is the circle here? Why is it a circle? We could do a lot of interesting mathematical conversations around this task if we really made these variables explicit. Another thing we tried was to first to put a coordinate grid underneath so that the position would become mathematically interesting or explicit. The position is, in the old code, it was 0, 0. And of course that didn't say anything on a blank screen. But once we put the coordinate system there, we could pinpoint where 0, 0 was, and then we could start change that. We could make that into a variable and make a program that would repeat. So here the drawing of the circle is in one code, and it's nested into another loop, which is then has another variable of moving the whole circle. So we get several circles. So this was just a way of thinking about what can we do with a task to make it more rich. And we said, do we think teachers are going to be able to do this? I think it takes a lot of knowledge about mathematics, about the program, about possibilities to be able to develop tasks like this. So to finish off, how can our research inform practice and curriculum development, and what are the potentials and challenges? Now what's my takeaway message here? Well, first thing is describe the knowledge to be taught clearly. If teachers don't know what they are expected to teach, they have to invent it themselves. They go out on Facebook, they find a group, and they say, what do you do? Well, that seems like a good idea. And how do we know who they're getting that information from? Make sure the teachers have the necessary competence. Of course. Supply teachers with research-based teaching materials and tasks. And this is ongoing. The problem with this is that the environments are changing so quickly that you come up with a really good task, you give it to teachers, and the next time they open the program, everything looks different. So this is a big challenge for us as well. And on a more general plane, give computational thinking and programming a status as a field of knowledge in its own right. not as something we just throw into algebra. It's important. I mean, I think that it's an important part of the knowledge of the 21st century, but it needs to be acknowledged as such. And for programming to be useful in mathematics, you need to know quite a lot of mathematics and quite a lot of programming. You should be aware of that and not think that you can make it really useful in perhaps primary school for mathematics. It can be useful for other things. And when we use it for what it's really useful for. Connect it more to handling large sets of data. That's where it's really powerful. That's where we should start, because then the students will see that it's useful. And in the future, is this going to be interesting at all? Or what is the knowledge going to look like that we need when we meet AI? ChatGPT is good at producing code, and it's good at explaining code. You can put a piece of code into it and ask the AI to say, tell me what happens in this code, and they will give you a fabulous description. And even notice its own errors. So it's good at that. So what do students need? If the AI can do that, what do students need to do? Well, they need to be able to tinker. They need to be able to think, well, what do I want the code to be changing? They need to be creative. So what are the future practices? And how much will be done in specific programming languages that we now teach the children? And how much will... I see it's a continuous scale from zeros and ones. Nobody uses that anymore. Nobody sits at the computer, or hardly anybody, I would say. Don't know of anybody actually programming with zeros and ones. Because we invent all these in-between steps of making it more user-friendly. And over here we have like GeoGebra. So where is the cutting edge? Where is it programming? Is it programming here, or is it programming here, or somewhere in between? And at what step is it important that people are able to go in? Do we need people in the community to be able to use GeoGebra? Do we need them to go in between, or do we need them over here for the basic programming? I'm not sure which, so this is an open question. Thank you very much for listening.
Thanks a lot, Cecilia. How strict is the time schedule? Are we allowed to have 1 or 2 comments? Or Charlotte? Charlotte says yes.
I will otherwise be available for the meet the.
Yes, we have the meetup as well.
Yeah.
Should we open up for 2 brief comments?
Thank you so much for your presentation. I'm curious on how you decided on the borders of the definitions of the different concepts, like what is mathematics and what is algebra. Because, for example, the task that you showed with the dancing, you said you decided that wasn't mathematics, but I might have said that it was, because it was pattern recognition maybe, and learning to play by some rules, and exploring, and I imagine that was really difficult. So how did you do it?
Yes, thank you. That's very good. And that goes back to my initial analysis of the logos for the teachers. So if you're in the middle group there, if you remember, if you see programming as being at the heart of mathematics, then of course that would have been coded as mathematics. We were more pragmatic. We coded things as being algebra. When we talked to teachers, we coded it as being algebra if the teachers interpreted it as algebra, if they talked about it as being an algebra task. And we coded things as not being non-mathematical if we thought that this is a task that they could be doing in school if we take away algebra if we take away programming in algebra in the curriculum. If you take that away, it's a great task to be doing. They could do it in technology lesson, they could do it in some other lesson. And the teachers didn't talk about it as being an algebra learning goal for it, or a mathematical learning goal at all. So that's why we call it no mathematics. We couldn't see that the teachers didn't see it, and we didn't see it, unless you define algebra, as you say, you can say that okay, there's some kind of pattern recognition here. Okay, then that's. I showed you one task in the textbook where we saw that there was a bridging between the pattern recognition and the programming. But in many cases, there was never such a bridge made. It was just, we do the programming. So that's a pragmatic definition.
Okay, I have a comment too. Thank you, Cecilia, for a wonderful talk. So my comment is slightly related. These things that you call stepwise instruction and describe as non-mathematical, typically, they remind me very much of these old Seymour Papert, how do you walk a code, which is like in a sense, pre-differential geometry activities and has been explored like this for a long time. So I found it weird that you called it non-mathematical, but is that because of the algebra focus or?
Well, I had a slide. I'd like to go back to it if we have the time, because I didn't say as much about it as I would have liked. It was one of those follow the instruction. Where is it? Oh.
That's
this one.
Yeah, this one for instance.
And I said, if we had just tweaked the question a little bit, if we had said, what geometric shape will be created here? What should change in the code if you want to draw a different shape? What will happen if you change the number of squares to move or the size of the turn? If you start asking that kind of questions, then it's a mathematical task.
No,
but just following this and drawing it and identifying it as a square, no.
Okay. But it's connecting representations and it is recognizing. Yeah, this is a good example.
Yeah, we get back to the fundamental question of what is mathematics.
Yes.
Thank you.
Okay. Thank you, Cecilia.
Oh, thank you very much. Thank you.